I'm going to talk through number 2 through 6 on today's practice worksheet. So first of all, number 2 here is not the type of question that would necessarily show up in a test or something. They're more just good things to think about. So for the first one, on the interval x such that, well, on the interval x, which is on negative infinity to infinity, list the largest intervals on which f of x is continuous. Largest just means you're not going to say, oh, it's continuous from -7 to 6, because that's really small, right? So we're going to look for the biggest ones. So it's continuous from negative infinity to -5. And then from -5 to -3, which is here. And these are x values, keep that in mind, these are intervals. And then again from -3 to 2. And again from 2 to infinity. So as far as the smallest value k, such that the function is continuous on k to infinity, we're really just looking for some interval that the function's continuous on that value. It's a terrible infinity sign, on that value to infinity. So if you kind of go along here, like, well, starting at -7, no, looks like we're moving over on the x's, moving over on the x's. Well, it doesn't work here. But technically starting at when x is 2, there's that hole there, it's continuous from 2 to infinity. So our k is just 2. As far as the smallest value such that the function's continuous on the closed interval, so this was open interval because it starts at 2, but 2 wasn't included. Down here, it's really any value that's infinitely close to 2. Because basically, I'm going to erase a little bit because it's got a little crazy looking. Basically, it doesn't work starting at 2. What if you started like at 2.1? It would be continuous from 2.1 to infinity, and that would be fine. Part D is actually also 2. Reason being, if you start at -3, so this asymptote here, the function's continuous from -3, moving along to where x is 2. It's continuous there. So continuous on -3 to 2, and 2 is included because it's closed. But it's not continuous on the interval from -3 to 2 plus 1, or -3 to 3. So that's our 2 is our b, so 3 would be our b plus 1. Because if you look at it, -3 to 2, it's not continuous because we'd have to jump up here to get to 3. Hopefully that was somewhat helpful. Again, this is more just something to think about than typical calc questions. Let's talk about number 3 through 6. These are typical calc type questions. So one thing to keep in mind, basically the only type of removable discontinuity is a whole. And that's where you factor something out. Well, basically factor the numerator and denominator of a fraction and cancel out a factor. That's your whole. Non-removable is a step/jump discontinuity. They're the same. Or an infinite discontinuity. An infinite discontinuity, or infinite to disc, is the same thing as a vertical asymptote. Absolutely the same. You can just call them both things. So looking at number 3, there's a 1 on top, so there's nothing we can cancel out. There's no holes. But what I do see, because if we're looking for discontinuities, it's essentially, are there any values that don't work in the function? And in this case, x can't be 3, right? So basically at 3, since we're not canceling anything out, we end up with a vertical asymptote right here when the denominator is 0. So x minus 3 equals 0. So at x equals 3, there's a vertical asymptote, which is the same as an infinite discontinuity. And keep in mind, to kind of prove that this is true, the limit as x approaches that vertical asymptote of f of x is going to be 1 over 3 minus 3 squared, which is 1 over 0, and 1 over a really small number in terms of a limit is just infinity, okay? But again, keep in mind that if you're finding an infinite discontinuity, it's just a vertical asymptote. Okay, over here, first step is going to be factor. Kind of when you see something like this, you just factor your polynomials. So the denominator factors into x minus 4 times x minus 5. So x minus 4 cancels, meaning there's a hole or a removable discontinuity at x equals 4. Because we can cancel it out. That's the key. It's removable, so you can cancel it out like that. And so our function now is 1 over x minus 5. So we have, if you set x minus 5 equal to 0, you end up with x equals 5 being your infinite discontinuity / vertical asymptote. And if you just straight up plug in a 5 here, 1 over x minus 5 is 1 over 5 minus 5. 1 over a really small number goes to infinity. So then the limit as x approaches 5 equals infinity. And that's how you prove that something is a vertical asymptote. Number 5 is one of those weird absolute value ones. And so basically what happens is we have to split it into our piecewise. And so h of x is either going to be a positive x plus 2 over x plus 2, which is 1, something over itself, or a negative x plus 2 over x plus 2, so a negative something over itself, which is negative 1. And then you have to look at kind of where it splits. So if we look at what's inside our absolute value, set that equal to 0. So this will split when x equals negative 2. So we're going to have an x and a negative 2 for both of these pieces. It's just which is less than and which is greater than. So let's check a value less than negative 2. Like if x is negative 3, let me go back up here again. Negative 3 plus 2 is negative 1. So if x is less than negative 2, we'll have a negative value. And if x is greater than negative 2, let's say negative 1. Negative 1 plus 2 is 1, which is positive, so this one has to be greater than. In terms of a graph, it'll just look like this. So it switches at when x is negative 2. And so when x is greater than negative 2, the value is 1. When x is less than negative 2, the value is negative 1. So it's a step or jump discontinuity at x equals negative 2. In general, except for like on the first page with that crazy piecewise with the asymptotes, in general, when it's piecewise, you will see a jump or step discontinuity. I don't want to say always because there really is no always in calculus, especially limits, but generally piecewise is where you see the jump or step discontinuities. So for number 6 here, basically, normally if you were checking for a discontinuity, you would do the continuity test. In this case, we kind of know there's going to be one because when you look at the instructions, like classify the type of discontinuity. But for the sake of argument, let's say we just want to check. So let's do the continuity test. So first of all, f of 2, because we're checking just our 2, is negative 1. The limit as x approaches 2 from the left is like less than, we look at the top function, 2 plus 1 is 3. The limit as x approaches 2 from the right of f of x is our bottom function, because right is greater. So 2 squared is 4, plus 1 is 5. So none of these values are the same. And if we think of a picture, it would be, well, f of 2 is negative 1. And then x plus 1 would just be this line right here. And then, actually, sorry, it would go all the way to 2. And then x squared plus 1. If you plug in the value, this would be at 5, and so I'm sorry, so there's a hole here. Okay, there's our line. It's not meeting where it looks like it, where the actual point is. And then for x squared plus 1, basically we'll go up to wherever 5 would be, and we'll have our parabola. So essentially these are not meeting, right? And I don't see an asymptote. So this is going to be a step or jump discontinuity at x equals 2.